Okay, grade 12. So now that you've seen that video of me playing billiards online, like I say, I'll take any challenges. If you guys want to have an online tournament, I'm up for that. I mean, we got a lot of time on our hands here. Okay. Anyway, I want to explain that now. Like, how does that work? Conservation of momentum, and this thing with collisions. That's actually a really big part of this unit. Okay, is doing collisions like this, and you'll see it's actually really straightforward. Okay, so what is conservation of momentum? What does that look like? And I've shown you a couple of pictures here, and I put this on OneNote. So let's just get started. We're going to start with one-dimensional example. Okay, but before I do that, I want to explain what conservation of momentum is, okay, and why it happens. Okay, first, before I do that, I have to tell you what an isolated system is. Now, I explained it in the billiards video, but I'll just write it down here. An isolated system, okay, that's a system where there's no influence from external forces. So the only forces, I'll just write therefore, the only forces are between objects in the system. Okay, now external forces would be things like gravity and friction and the normal force and everything else. But if those things sort of cancel out, then we have an isolated system. Basically, we can treat all collisions like momentum is conserved, okay, and it's an isolated system. Like even two cars crashing where there's a lot of friction, and you might think that it is an external force, friction, but the thing is that if you look at immediately before the collision and immediately after, momentum will be conserved in those instantaneous sort of moments. Okay, so this is kind of a very useful thing. Like if you were going to aim to forensic science, you need to understand this. Okay, it's actually a big part of it. Okay, so there's a lot of physics in forensic science, and this conservation of momentum, ballistics and stuff like that, that's what it's all about. But anyway, let's not get ahead of ourselves. So that's the definition of an isolated system. In an isolated system, momentum must be conserved. Let me explain why. Okay, I'm just going to say consider a collision between two masses. Okay, and I need to move that thing out of there. Let's mark for the next thing. Pardon me while I move this little picture out of the way. Okay, so consider an isolated system between two masses. The isolated system we'll have here, I'll give you a little example. Let's say you have a little cart here, and that's going this way. I'm going to call that M1, and I'm going to call this V1. Okay. Now, there's another guy, and he's going this way. We're going to call this M2, and we're going to call this V2. Now, remember before, these are vectors, so I'll put little vector hats. Remember before when I said, like, we're not going to use V2 to mean the final velocity? See, this is why. V2 represents the initial velocity of mass number 2. So like whenever you see a little subscript 2, it means that quantity goes with mass number 2 in the collision. And here, this V1 here, that goes with mass number 1 in the collision. Okay, so the little subscripts identify which mass that we're talking about for the velocity. So we don't want to use V2 to represent the final velocity of one of the masses. It's actually the initial velocity of mass 2. Mass 2's final velocity is going to be V2 prime, and that's the prime notation. It means final velocity, and the subscript means which mass it goes with. All right, so look, when they collide, okay, during the collision, if I draw a little free body diagram of M1, it's going to look like this. Okay, yeah, there's gravity. Yes, there's a normal force. They cancel out anyway, we don't really care. But mass 2 is going to push that force, that object this way. Now I'm going to label this, it's going to look a little weird, force 1, 2. It means the force, sorry, let me change that, the force of 2 on 1. It's the force of mass 2 pushing on mass 1. Now the only way mass 1 can accelerate is that way. Now it doesn't mean it's going to move that way. It means it could be slowing down. So it could be moving forward still, like to the right, let's say, but slowing down. That still would mean an acceleration to the left. Mass 2 can only push it to the left, so that should be logical to you, okay? All right, now if I draw a free body diagram of mass 2, it looks very similar. Yeah, whatever, we'll put the gravity, it's there after all. They cancel, that's why it makes it an isolated system, because these two cancel. This is the force of 1 on 2, and that's going to make that guy accelerate that way. Okay, so here we have our two free body diagrams. We see that they look very similar. They both experience a force in opposite directions. That's what happens during a collision. Okay, but because of Newton's third law, remember the third law says for every action there's an equal and opposite reaction. Well, that means we know something about these two forces. We know that the force of 2 on 1 is equal to the negative of the force of 1 on 2, right? We know that because that's the third law, that, you know, for every action force, there's an equal and opposite reaction force. So this force between them has to be the same size. One can't push harder on the other, like it's always the same. And some people get confused with that. Let's say M1 is a huge truck and M2 is this tiny vehicle. When they collide, you're thinking, oh, the huge truck exerts a way bigger force on that small car. That's not true. The force of impact between them is the same. They both experience the same amount of force. What's not the same is the acceleration, though. These two accelerations are not going to be the same number. So this is the acceleration of mass 1. This is the acceleration of mass 2. That's not going to be the same. That will depend on their mass. But these two forces, I'll circle them in green, that one and that one have to be the same size. That's Newton's third law, okay? So now what I'm going to do is I'm going to multiply both sides by time. So I'm going to go F21. After all, the amount of time they're in contact is the same for both also. F12 times time, okay? So you see what I did there? Oh, and once again, I got to move this little turkey out of the way. I'm writing too big. It's hard for me to write on my screen. FYI. It's way easier on the smartboard. All right. So what I did was I just multiplied both sides by time. I'm allowed to do that. I haven't broken any mathematical rules. The time in contact must be the same on both sides. Now we know this is impulse. So the impulse on each side equal and opposite, right? Now, what I'm going to do is I'm going to write down, I'm going to insert the other definition of impulse, which is the change in momentum. So I'm going to go mv1 prime minus mv1 equals negative mv2 prime minus mv2. So what I did was I substituted in the change in momentum. This is the change in momentum here. I'll circle it in green or underline it in green. That's the change in momentum of mass 2. And this guy is the change in momentum of mass 1. The negative sign here stays with that one, but there's no negative sign on the other side. Okay. Now what I'm going to do is I'm going to just group my terms. I'm going to bring everything that has a prime in it. Prime, just remember, means final velocity. So I'm going to bring everything that has a prime on it on the left side of my equation, and everything that is not primed I'm going to bring it to the right side. Okay. So what I end up with is this. If I do that, I get m v m1. That should be an m1 there. Pardon me. And this should be an m2. Okay. So m1 v1 prime, and then when I bring this to the other side, it's going to be plus m2 v2 prime, like that. And that has to equal, now negative and a negative cancel out, so I get m. I'm going to just put it in the same order. When I bring that to the other side, it becomes positive. m1v1 plus m2v2. All right, I'm going to circle this equation because it's very special. What is this telling us? Well, the final momentum of mass, the first mass, is this expression right here. That's its final momentum. I don't like that. Let me undo that. This is its final momentum right here. I don't like that again. Okay, there you go. That's its final momentum. And the final momentum of mass 2 is this guy right here. Well, the sum of those two things, so this is the final momentum of mass 1 and the final momentum of mass 2, they add up to the initial momentum of mass 1 plus the initial momentum of mass 2. So what are we seeing? Well, we're seeing, I'll write it in words, that the final momentum, this is after the collision takes place and they have their final velocities, equals the initial momentum. And that tells us, therefore, that momentum is conserved. Isn't that amazing? Okay, so we just figured out Newton's law of conservation of momentum. Now, it's not one of the laws of motion or one of the four laws, the four sort of primary laws, but it's as a result of Newton's third law. Okay, so momentum must be conserved. And this is actually a really useful thing. It allows us to solve problems that we never could have solved without it. Okay, so let me give you an example. Okay, so I'll give you a couple of examples. So number one, we call this an inelastic collision. What happens when, let's say I throw a ball of dough at you, okay? And the ball of dough is sticky, so it sticks to you. And like if we were there in class, I would definitely throw a ball of dough at you because it's such a fun thing to do. I love doing that. So what I do is, like, when you least expect it, I get the sticky ball of dough and just throw it at you, okay? It lands on your back. I'm sure, like, you know, someone would be shocked by this, but you know, it's me. I have to do that. And it's too bad because of the pandemic, I can't really throw a ball of dough at you, but just picture in your imagination, okay? Now, because the dough sticks to you, we call it inelastic. Elasticity is the tendency of an object to reform its shape when it gets deformed, and dough definitely doesn't have it, okay? So that's why when you throw it on the wall, it sticks to the wall, like it gets deformed and stays deformed, okay? So sticky collisions tend to be something we call inelastic, okay? So an inelastic collision. Let's say I throw this ball of dough, okay? You're standing over here. All right, let's say this is like your Anastasia with her top knot here, like that. And there she is, waiting for this ball of dough to hit her. Okay, so here comes the ball of dough. The lights are on. She can see them. It's all good. Okay, and let's say this is a huge ball of dough. Let's say it's 10 kilos. Okay, and let's say it's moving at 40 meters per second. That's going to be really an amazing sight, okay, to see this. She's sitting here. She's not moving at all. So let's call this M1. She's M2. And here her V2 is 0. Oops, that's a terrible 0. 0. Okay? So that means her initial velocity is 0. Now, what's going to happen is, let's say there's no friction. So let's say this is slippery. Okay? And so she's not moving right now, but for sure, when that ball of dough sticks to her, she's going to start moving. And the only real way she can move is to the right. I mean, it's coming in, it's moving to the right. When it hits her, it's going to hit her, it's going to sort of stick onto her, and she's going to, together, a combined mass, they're going to move. Now, let's say her mass is a very normal 40 kilograms, okay? So 40 kilograms, and she's being hit by this 10 kilogram ball of dough, which is like 20 pounds of dough. All right, so my question for you, again, I have to move this guy. So let me this out of the way one last time. That's really for the next lesson. I should have put that in the next one. All right, so look. An inelastic collision takes place. The thing is here is what is v prime? What is the final velocity? So she gets walloped by this ball of dough. What's her final velocity? Okay, now in fact, they're both going to have the same velocity because when it sticks to her, they're going to move together like one mass. Okay, so that's an important thing to remember, right? If something sticks to you, now you're kind of part of each other, right? You're now moving as not two separate masses, but one mass. So it's the same thing if you catch something. Okay, catching something is an example of an inelastic collision too. All right, so look, how do you do this? Well, we'll just use the law of conservation of momentum. It's very straightforward. So we consider this an isolated system. Gravity and the normal force will cancel out, and there's no friction. So it's only the forces between her and that ball of dough, Anastasia and the ball of dough, all that matters. All right, so let's go ahead and do it. We know that m1 v1 plus m2 v2 has to equal m1 v1 prime plus m2 v2 prime. See, that's the law of conservation of momentum. The initial momentum equals the final. Okay, it doesn't really matter which order you put it, but initial equals final. Okay, prime means final velocities, and unprimed means initial velocities. And here the subscript just means which mass the velocity goes with. All right, so here m1 is 10. Okay, v1 is 40 plus 40 kilograms times 0. She's not moving at first, right? Equals, now here's the thing, because they stick together, v1 prime and v2 prime are going to be equal because they're going to move as one mass. So let's not pretend they're two different things. We're going to treat them as one variable. So what you get is, if you just group your like terms, they're combined, their mass now. Okay? So the ball of dough is 10, she's 40, so that's a total of 50 kilograms times v prime equals 10 times 40 over here, which is just 400. All right, so let's do it. So 400 equals 50 v prime. And what is that? I'm so tired. Okay, here, hang on. 400 divided by 50 is what, 8? Yeah, I think it's 8. So 400 divided by 50 is 8, yeah. Wow, my brain is like turned off. Okay, so you get v prime equals 8 meters per second. Now, you got a positive number, so they're still moving to the right. Okay, of course, she's going to get hit. Now, what happened was the ball of dough slowed down. It was moving at 40 meters per second. Now it's moving at 8. And she sped up. She was at 0, and now she's moving at 8 meters per second, just like the ball of dough. And then that's logical, right? For the ball of dough to slow down and for her to speed up. Okay, and now together they move off to the right at 8 meters per second. And that is an example of how you do a one-dimensional conservation of momentum problem. Okay. Now I can show you another one. I might as well show you this. It was on the final exam last year, so here's another example. Okay, number 2. This sort of reverses it. Let's say you have, here's mass 1, and there's a spring, and there's mass 2. Okay, like that. And I'm going to say this time that the two masses, I'm not going to tell you what they are. We're going to keep it a secret. I'm going to tell you that mass 1 and mass 2, we don't know what they are, but they're the same number. Okay? So what we'll do is we'll just call them M, not M1 and M2 anymore. Okay? All right, so now what we're going to do is we're going to take these two masses and we're going to squeeze them together with a spring in between. And then I'm going to let go. Okay? And so what happens is initially v1 is 0 and v2 is also 0. But then when you release it, v2 prime that mass m2 is going to move off to the right, and v1 prime is going to be in that direction. So once they're released, the spring will impart momentum to them. Okay, there's that stupid thing coming up again. But anyway, well, there's probably enough room to do this. Okay, so if I give you one of these things, so let's say I tell you that v2 prime was equal to 15 meters per second. Could you find v1 prime? What's this one then? Okay, so I'm going to circle it. What is that one? Okay, we know this one. So this is the given information. What's the other one? So again, just use conservation of momentum. m1 v1 plus m2 v2 equals m1 v1 prime plus m2 v2 prime. Okay, and then what you do is, at first, these are both 0 because the initial velocities v1 and v2 are both 0. So now, over here on this side, we're going to get m times v1 prime plus 0 equals m times v1 prime plus m times v2 prime. Or here, I'll just put 15. Okay, for v2 prime. Okay, now solve it for v1 prime. Well, just bring this to the other side. You get m times v1 prime is equal to negative m. What was I writing here? This should be just 15. Okay, negative m times 15. Now the m will cancel because they're equal, and you're left with v1 prime equals negative 15. Now, what does the negative sign mean? Well, if this way was the positive direction, this was the direction of v2 prime is in that direction. Well, which direction is v1 prime? Well, clearly, it's in the opposite direction, right? So v1 prime is moving that way. That's v1 prime moving in the negative direction. Okay, and we can, so remember these are vectors. So that's what the negative sign means. It means it's the opposite direction. Okay, so it's moving to the west, if you like, and the other one's moving to the east. So there you go. That's how you do conservation of momentum in one dimension. In the next video, I'll explain how to do it in 2 dimensions. And then we're ready for our first quiz, and that is very exciting to do online. I'm still trying to figure out how I'm going to test you guys, but trust me, I will figure it out somehow. Okay. All right, so let me stop.